Hello everyone. I hope all are good. So the topic we are going to discuss today is electrostatic potential and capacitance CBSE PYQs. Disclaimer: the images, text and other material used in our presentation are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So our first question is: equipotential surfaces at great distance from a collection of charges whose total sum is not zero are approximately. So in space there is a collection of charges, means a number of charges are present in any configuration, in any formation. We don't know the formation, but their total sum is not zero, means there can be positive charges also, there can be negative charges also, but their collection, the total sum of all the charges is not zero, it is non-zero value. Okay, either it is negative, net charge is negative, either net charge is positive, but not zero. And the equipotential surface from this collection of charges at a great distance. So we are viewing this collection of charges from a very great distance, from very far point. So how the equipotential surface due to this collection of charges will look like? Okay, so approximate result we have to give. Okay, so what are the options here? First option is sphere. We will see the equipotential surface as sphere, or we will see these equipotential surfaces as planes or paraboloids or ellipsoids. So these are the four options that this shape can be viewed for a collection of charges. So which is correct, you have to tell. So I will give you some time to think about it. Okay, so what is the answer? Answer is A, spheres. Why spheres? Because this is the collection of charges. Take an example of bunch of grapes. Okay, so there are bunch of grapes on the vine of the grape. Okay, so if we are viewing this bunch of grapes from a from a large distance, from a great distance, so the bunch of grapes will look like a point like object. Okay, or there may be some small pebbles, they are collected at some point. Okay, so very small pebbles are placed in the form of a collection, and if we viewing these charges from a great distance, then it will look like a point if we are viewing from a great distance. Okay, similarly, our earth, okay, it is viewed from a very distant planet, it will look like a point object. Or our solar system, if it is being viewed by any other galaxy or any other point on the same galaxy, so it will look like a small point. So only the distance matters here. So if we are viewing these things from a smaller distance, we will resolve the different objects, different charges in the collection of charges. If we are viewing from a larger distance, we cannot resolve the different charges present in the collection. We will assume it as point charge. Okay, so this is point charge, it is assumed to be point charge. So due to point charge, what are the equipotential surfaces? That are spheres. So approximately the equipotential surface will be sphere. So equipotential surfaces at a great distance means that space of charge is negligible as compared to distance. Means the space where charges are collected is very small as compared to the distance from where we are viewing these collection of charges. So the space of charges is negligible as compared to distance. So the collection of charges is considered as a point charge. So these collection of charges can be considered as a point charge. Okay. So electric potential due to point charges. So we know that electric potential due to point charges V equal to KEQ by R. So this is the formula for potential due to a point charge at any distance R. Okay. So if we fix this R, okay, so if we around a charge, if we fix this R, so in any direction, this is same R. So by joining the locus of these points, we will attain the which surface? Sphere. Okay. So what is the locus basically? Locus is the surface or any curve that is formed due to putting some condition and joining the points. Okay. Which explains that electric potential due to point charge is same for all the equidistant points. So for that point charge, if this is a point charge, so a distance R from this point charge, if we fix this R, so there will be charges around, there will be some points around this charge. Okay, for a fixed R. So if we connect these points in 2D, it will form a circle. So by putting a condition and attaining some points and after joining these points, it is called locus of these points. Locus is the curve that is formed by joining the points, putting some specific condition. Okay, or in 3D, what will be formed? Surface. Okay, in 2D it will be circle. Okay, in 3D it will be sphere around a point charge, which are at same potential. Okay, the locus of these equidistant points which are at same potential form spherical surface. Okay, so we will assume collection of charges as point charge because we are analyzing these collection of charges at a great distance from it. So the space of charge is negligible as compared to distance. So we'll assume it as point charge, and potential for point charge is this. And after fixing this R and all the connecting all the points that are equidistant from this point charge, the locus of these equidistant points which are at same potential forms spherical surface. And this spherical surface is equipotential surface for these collection of charges. Okay. So our next question, physical quantity having SI unit Newton per coulomb meter is. Okay. So we know that Newton per coulomb is the unit of electric field. But here they have given Newton per coulomb meter. Okay, so we have to see what of which physical quantity this SI unit is. Okay, so I will give you some time to think about it. So the answer is electric potential or potential difference or EMF. EMF we are going to discuss in detail in next chapter, current electricity. Okay, electromotive force. So for now in this chapter, potential difference and electric potential. This Newton per coulomb meter is unit of electric potential. How? We will see. Unit of electric potential is volt, which is equal to, electric potential is equal to work upon charge, isn't it? So electric potential is the work done to bring a unit positive charge from infinity to any point in the electric field of that charge. Okay, so what is work done? What is potential energy? Potential energy is work done in bringing a charge from infinity to any point. So in potential, we replace any charge with unit positive charge. Okay, means work done upon charge. Okay, so unit of electric potential is work upon charge. That is, unit of work is, or potential energy is, joule upon coulomb. Okay, unit of charge is coulomb. So what is joule? Joule is work is equal to force into displacement. Okay, so unit for work is joule, which can also be represented as Newton meter. Force into displacement. Okay, so Newton meter upon coulomb. Okay, so it will give us Newton per coulomb meter. Okay, understood how this came? Newton per coulomb meter. And also we can find that Newton per coulomb meter is unit of which physical quantity by this thing. We know that Newton per coulomb is unit of electric field. We know that the relation between electric field and electric potential is what? E equal to minus dV by dr. Okay, so dV by dr. dV is potential difference. Okay, having unit volt. Okay, upon dr, which is distance. Okay, so it is of unit meter, and electric field having unit Newton per coulomb. So dV, that potential difference, will have unit Newton per coulomb, and dr will go there in both ways, E equal to minus dV by dr, and in this way. In both ways we can find the unit of physical quantity having unit SI unit Newton per coulomb meter. Okay, I hope you understood. Next question. Prove that a closed equipotential surface with no charge within itself must enclose an equipotential volume. Okay, so what this question means, that prove that a closed equipotential surface, okay, equipotential surface that is closed, like sphere or any other shape that is closed. Okay, so we have to prove that closed equipotential surface with no charge within itself, having no charge within itself, okay, must enclose an equipotential volume. Means that equipotential surface with no charge within itself must enclose a volume which is at constant potential. Means inside that equipotential surface, inside this equipotential surface, in bulk of the body, there must be constant potential. So it must enclose an equipotential volume. So this is the question. So I will give you some time to think about it. So let's see the solution. So according to Gauss law, okay, if there are no charges enclosed by the surface, the net electric flux through the surface is 0. Mathematically, this is expressed as, okay, so according to Gauss law, if there are no charges enclosed by the surface, the net electric flux through that surface is 0. Okay, so if there is a surface or there is no charge within, okay, so this first condition, if there is a closed equipotential surface with no charge within itself. So if there is a surface with no charge within itself, so net flux through that surface is 0. Mathematically, this is expressed as, so according to Gauss law, this is the mathematical expression. So flux through any surface that is enclosing no charge, there is no charge within that surface, okay, so electric flux through that surface is 0 always. Okay, so electric flux is equal to closed integral over the surface E dot ds electric field and area element equal to Q enclosed by epsilon naught. So electric flux through any surface, enclosed surface, is Q enclosed by that surface and epsilon naught, that is constant, is equal to 0 if Q enclosed is 0. If there is no charge within that surface, then this electric flux will be 0. Okay. Since Q enclosed is 0, so since Q enclosed is 0, that's why flux is 0. Okay. And also, if this flux is 0, means that closed integral over surface E dot ds is always also equal to 0. Okay. So area element cannot be 0. Area cannot be 0. We have selected some area. This means the electric field is 0 in that point or on that, inside that surface. Okay. Since Q enclosed equal to 0, it implies that electric field must be 0 everywhere inside that surface S. So this term will also be 0 because ds, we have selected some area element and area of this element is not equal to 0. So this means that electric field inside that surface is 0. The electric field is now related to the electric potential V by the equation. So now this electric field is related with potential. How? With what equation? The equation is E equal to minus dV by dr. Okay. So this is negative gradient of potential. What is gradient? This inverse delta sign, this is d by dr. Okay, this inverse sign is d by dr, means, so this thing is called gradient, d by dr. Okay, so electric field is negative gradient of potential difference. So if electric field through any surface is 0, this is equal to 0, then this means that gradient of the potential V is also 0. This means this whole term is equal to 0. dV by dr minus dV by dr equal to 0 and dV by dr equal to 0. If the gradient of any term, or we can say differentiation of any term with respect to any quantity is equal to 0, this means that quantity that is in derivative in numerator will not change. That is constant. Okay, derivative is dV is what? Variation in the potential, small change in the potential. So if it is equal to 0, it means that dV is equal to 0, means there is no variation in the potential, there is no change in the potential, so that potential is equal to constant. Okay, so if electric field is 0, this means this dV by dr equal to 0. dV by dr equal to 0 means that V quantity is, that potential is constant everywhere inside that surface. So if the electric field E is 0, this means that gradient is dV by that is d by dr. Okay, so gradient of potential V, so gradient of potential means dV by dr. If we are specifying that only gradient, that is d by dr. Okay, so gradient of any physical quantity means differentiation of that quantity with respect to the distance of displacement, dr should be there in the denominator. Okay, so this means the gradient of potential V is also 0. Therefore the potential must be constant throughout the volume enclosed by the surface S. Okay, so dV by equal to 0, which means V equal to 0, which means V inside that equipotential surface that we have taken initially is 0. So over the volume enclosed by this equipotential surface with no charge, there is constant potential inside the body or in the bulk of the body. That means that equipotential must enclose an equipotential volume. Okay. Next question. Write two properties by which electric potential is related to the electric field. So you have to mention any two properties which electric potential is related to electric field. Okay, so first one is the relation. So we have to interpret this relation, that what the relation of electric field and electric potential represents. So that are the two properties by which electric potential is related to the electric field. So I will give you some time to think about it. So let's see the solution. Two key properties related electric potential and the electric field. First one is electric field is the negative gradient of the electric potential. Okay, so we find the electric field with the help of the gradient of the electric potential and after putting the negative sign. That means negative gradient of the equipotential surface. Okay, so what is the magnitude of the electric field and what is the direction of electric field? That two things are being shown by this relation. Okay, the mathematical equation for the electric field as the negative gradient of the electric potential is given by this equation. E is equal to, with direction, equal to minus negative gradient of potential minus dV by dr. Okay, so this negative sign shows the direction of the electric field and this gradient of dV is showing the magnitude of the electric field at any point in the space. Okay, so where E is equal to electric field vector and delta V is gradient of the electric potential. Okay, so gradient of variation of potential difference with respect to variation of the distance in the space or the difference between 2 points or the distance from any source from where electric field is being generated is equal to the electric field. So difference, potential difference upon displacement or difference in 2 points, separation of 2 points. Okay, so this is showing the electric field in that region. So if a region is bound by 2 points, the potential difference of between these 2 points upon the separation between these 2 points is equal to the electric field. This is the magnitude of electric field. Okay, so dV by dr shows the magnitude of the electric field. Now this negative sign is showing what? We will see. So the second thing, electric field is directed along the direction of decreasing potential. Okay, so electric field is directed along the direction of decreasing potential, means this dV by dr and this negative sign shows that electric field is in the direction where potential is decreasing. Okay, so in the direction in which potential is decreasing, electric field is there. Okay, electric field, if there is a positive charge, electric field is radially outwards. Okay, so direction of electric field is in the outward direction, radially outwards. So if we move from that positive charge to radially outwards, potential will decrease. Okay, in the direction of electric field. So as we move away from this positive charge, potential will start decreasing. So this means electric field is in the direction of decreasing potential. That this negative sign is showing that thing. Okay, so these are the two properties by which electric potential is related to electric field. Okay, next question. A positively charged particle is released from rest in an uniform electric field. The electric potential energy of the charge is. Okay, so positively charged particle is there and it is released from the rest in an uniform electric field. So in a space there is electric field which is uniform and we are releasing a positive charge particle from rest, the electric potential energy of the charge. Okay, so let's see the option. Remains constant. Electric potential energy of the charge remains constant because the electric field is uniform. First option. Increases because charge moves along the electric field. Decreases because charge moves along the electric field. Or decreases because charge moves opposite to the electric field. So we know that if we place positive charge in any electric field, uniform electric field, it will experience force in the direction of electric field. So it will move in the direction of electric field. Okay, so will potential energy decrease or increase? We will see. Okay, so I will give you some time to think about it. So let's see the solution. The answer is C. Decreases because the charge moves along the electric field. That we already know that positive charge will move in the direction of electric field. Why is it is decreasing? Let's see. Direction of electric field is always perpendicular to one equipotential surface maintained at high electrostatic potential to the equipotential surface maintained at low electrostatic potential. Okay, so we know that electric field is in the direction of decreasing potential. Okay, by the relation of electric potential and electric field. So that we know that potential energy is equal to Q into potential difference. Okay, so for Q, that positive charge, it is constant. So potential energy will directly proportional to the electric potential. Okay, so if electric field is in the direction of decreasing potential, so it is in the direction of decreasing potential energy in this case. Okay, so what is the direction of electric field? It is always perpendicular to the equipotential surface. Okay, that we have already mentioned why. Okay, so it should be perpendicular to equipotential surface because we don't want any tangential component along the equipotential surface that will cause movement of charges on the equipotential surface. Then if there is a movement of charges or any tangential component along the surface, we will have to do work to move any point charge on the equipotential surface, which will violate the rule. Okay, equipotential surface potential is constant all over. Okay, so we don't have to do any work on the equipotential surface. So electric field must be perpendicular to equipotential surface. So now direction of electric field is always perpendicular to one equipotential surface maintained at high electrostatic potential to other equipotential surface maintained at low electrostatic potential. Okay, so the positively charged particle experiences electrostatic force along the direction of electric field. Okay, so it will experience electrostatic force along the direction of electric field from high electrostatic potential to low electrostatic potential. This does the work is done by the electric field on the positive charge. Hence, electrostatic potential energy of the positive charge decreases. Okay, also we know that work done, if the work is done by the conservative forces, then the change in potential energy is negative, means the final energy potential energy is less than the initial potential energy if the work is done by the conservative forces. We know that electric field is conservative and the force acting due to this electric field is also conservative. So the work is done by the electric field on the positive charge. So work is done by this electric field and the force is being applied on this charge which is conservative. So potential energy is decreasing. Change in potential energy is negative, means final energy minus initial energy is negative, which means final energy is less than the initial energy, which means potential energy is decreasing. Hence, electrostatic potential energy of the positive charge decreases. Got it? So our next question, define electric potential and electric field. How are their SI units different? Okay, so we have to define electric potential and electric field and show that how are their SI units different. So I will give you some time. Solution. Electric potential at a point is defined as the amount of work done in bringing a unit positive charge from infinity to that point in an electric field. Okay, so when we define potential energy, we are saying bringing a positive charge, not unit. Okay, so we eliminate this unit word in the definition of potential energy because we also take into account the amount of that positive charge. Okay, but in potential we don't take in amount that magnitude of this positive charge. We only define potential with the help of, we eliminate the charge of the test charge. Okay, we eliminate the magnitude of the test charge, so we will take unit positive charge having magnitude unity 1 coulomb. So electric potential at any point is defined as the amount of work done in bringing a unit positive charge from infinity, where at infinity potential is assumed to be 0, to that point in an electric field without acceleration, without any change in the speed. Why? Because we don't want any change in kinetic energy. We want all of the work done to be stored in the form of potential energy. We don't want any complexation, any complex things in the equation. So we don't want to take into account the change in kinetic energy, which will make the equation complex. So we want to store the whole work done in the form of potential energy. So we are moving this charge without acceleration, without change in the velocity. Okay, so its SI unit is volt. Okay, which is equivalent to joule per coulomb. We also know work upon charge. Electric potential is equal to work upon charge. So its SI unit is joule per coulomb, also known as volt. And one more unit we have discussed in previous question, Newton meter per coulomb. This joule can also be written as Newton meter. So Newton meter per coulomb can also be the unit of electric potential. Electric field at a point is defined as the force experienced by a unit positive charge placed at that point. Okay, so also in electric field we take unit positive charge, but in electrostatic force we take into the account magnitude of that positive charge. So how we find electric field or how we find the electrostatic force? Equal to Q into E. Okay, Q is the charge of test charge. Okay, so in electric field we don't take into account the magnitude of the charge. We assume that the test charge that is being moved, that is being displaced near this source charge is of 1 coulomb, unity charge. Okay, so electric field is defined as the force experienced by the unit positive charge placed at that point. Okay, so SI unit is the Newton per coulomb, or according to its relation with potential difference, which is equal to E equal to minus dV by dr. So potential difference upon separation. So what is this? Volt per meter. So according to that relation, unit of this electric field can be volt per meter and Newton per coulomb. Okay, so while electric potential measures energy per charge, electric field measures force per charge or potential difference per unit distance. Okay, electric potential measures energy per charge and electric field measures force per charge. Okay, So next question, which of the following is not the property of the equipotential surface? Okay, so not the property of equipotential surface. So first one is they do not cross each other. Is this property of the equipotential surface or not? Second option is the rate of change of potential with distance on them is 0. Okay, minus dV by dr is equal to 0 on the equipotential surface. So rate of change of potential with distance means dV by dr, which is equal to electric field. So electric field is 0 on the equipotential surface. Is it true or not? Third, for a uniform electric field, there are concentric spheres. If uniform electric field is present in the space, are equipotential surfaces in the form of concentric spheres or any other shape? Okay. Or fourth option is they can be imaginary spheres. So can equipotential surfaces be imaginary spheres? Okay, so these are the 4 options. I will give you some time to think about it. So correct option is C. So this, for a uniform electric field, they are concentric sphere is not the property of equipotential surfaces. We know that for a uniform electric field, equipotential surfaces are of what shape? Of a parallel planes perpendicular to the direction of electric field. Okay, so this option is correct. Means this thing, for a uniform electric field, they are concentric sphere is not the property of equipotential surfaces. Okay, so in a uniform electric field, equipotential surfaces are of which shape? Are flat parallel planes that are perpendicular to the electric field lines. Okay, so how can we represent them? If the electric field is directed along the x-axis, assume if electric field is directed along x-axis, the equipotential surfaces would be parallel to yz plane. Okay, if electric field is in the direction, is in x-axis, is in the direction of x-axis. So what is yz plane? This is yz plane. This is yz plane. Okay, so this is the direction, this is the direction, x direction is of electric field. So equipotential surfaces will be on what plane? yz, y and z. Okay, so they are parallel planes, flat parallel planes perpendicular to the direction of electric field. Okay, so if electric field is directed along x-axis, equipotential surface would be parallel to yz plane. These surfaces represent location where the electric potential is same at every point. So for any equipotential surface, electric potential is same at any point or at every point. Okay, so why they do not cross each other? According to first option, why is it property of equipotential surface that they do not cross each other? Because if they cross each other, there would be a point in the space where there is a 2 values of potential. If they cross each other, so at the point of intersection, there will be 2 values of potential at a point, which is not possible. At any point, there will be 1 value of potential. Okay. Also, the rate of change of potential with respect to distance on them is 0. Okay, dV by dr equal to electric field is 0. This is true. This is the property of equipotential surface. Electric field is 0 on the surface of equipotential surface, or only perpendicular component exists, not the tangential component. They can be imaginary spheres. This is also true. They can be. Okay, they must not be. Okay, they can be of any shape, but they can be of concentric sphere, imaginary concentric spheres in the case of point charge. Okay, I hope you understood. So next question, calculate the electric potential due to a point charge. How do you find the electric field from it? Okay, so calculate what is the electric potential due to point charge. How do you find the electric field from it? You already know. We have done the question like that. Okay, so I will give you some time to think. So let's see the solution. Electric potential V at a distance R from a point charge Q is given by. So we know that what is the potential energy stored when we move a point charge from infinity to any point at a distance R from the source charge is equal to 1 by 4 pi epsilon naught magnitude of source charge into magnitude of test charge upon the distance between the source charge and the point where we have to find electric potential energy. So in potential energy, we used to set the magnitude of test charge equal to unity, 1 coulomb. So it will eliminate from here. So this Q is the magnitude of the source charge. So electric potential at a distance R from a point charge, that is source charge, Q is given by 1 by 4 pi epsilon naught Q upon R. Okay. So where epsilon naught is the permittivity of free space. To find the electric field, what can we do? We know that relation between the electric field and potential is equal to minus dV by dr. Or we can say we take the negative gradient of the potential with respect to distance. Okay. So E equal to minus dV by dr equal to minus d by dr. What is the value of V? 1 by 4 pi epsilon naught Q upon R. So this 1 by 4 pi epsilon naught and this Q, they are constant, they will come out from the derivative. Only 1 by R will remain inside the d by dr derivative. 1 Q by 4 pi epsilon naught is constant. They will come out of the d by dr. Only 1 by R will remain here. So derivative of this 1 by R with respect to differentiation of this 1 by R with respect to R is minus 1 by R square. Okay, differentiation 1 by R with respect to R, differentiation is minus 1 by R square. So minus is already present here, and minus 1 by R square, minus sign will cancel out. So it will become Q by 4 pi epsilon naught R square. So this is the energy, electric field, which is the negative gradient of the potential with respect to distance. This is the standard formula for the electric field due to point charge. Due to point charge, we know that electric field is given by this formula. This is standard formula. It shows the electric field is the rate of change of potential energy with distance and always points away from positive charge towards the negative charge. We also know that direction of electric field is from positive charge towards the negative charge, and it is given by rate of change of potential with distance, dV by dr, and minus sign shows the direction. It is in the direction of decreasing potential. Got it? So thank you. I hope you enjoyed the session. This is all about today.